Tonight, we're going to talk about 3 planets: Venus, Mars, Earth. All 3 formed from the same cloud of gas and dust, at roughly the same time, orbiting the same star. All 3 started with water. All 3 started with thick atmospheres. All 3, for billion years ago, had the potential for life. 2 of them are now completely dead. One of them is covered in forests and oceans and cities, and is currently spinning through space at 1,600 kilometers per hour, while you lie still and listen to someone talk about astronomy. What happened? What went wrong with 2 of them? And what exactly, precisely, specifically, is the difference that kept Earth alive? The answer that most science classes give you is distance from the sun, the Goldilocks zone. Venus is too close, too hot. Mars is too far, too cold. Earth is just right. Simple, satisfying, done. But here's the problem with that answer. And this is the thing that stopped me cold when I first really thought it through. The moon is in the Goldilocks zone. Exactly the right distance from the sun, exactly the same solar radiation as Earth. And it is one of the deadest objects in the solar system. No atmosphere, no liquid water, no magnetic field. Temperatures swinging from 127 degrees Celsius in sunlight to minus 173 at night. A barren, airless, silent rock. Right next to us. Right in the middle of the Goldilocks zone. So the Goldilocks theory, on its own, cannot be the answer. It is not even close to being the whole answer. And tonight we're going to find out what the real answer is. By going back to the exact moments each planet crossed its point of no return. The moment Venus became a furnace. The moment Mars became a desert. The specific chain of events. The exact science. Because understanding why they died is the only way to truly understand why we are still alive. And why that fact is far more extraordinary and far more precarious than most people realize. Get comfortable. This is going to be a long, slow, wonderful journey. Every fact tonight is verified against peer-reviewed scientific literature. Nothing is speculation. Everything has a source. Now it is your time to stay alone with curiosity. The Goldilocks theory and why the moon destroys it. Let me start with the theory itself, because before we can dismantle it, we need to understand what it actually says and why it is so appealing. The habitable zone, sometimes called the Goldilocks zone, is a concept in astronomy that describes the range of distances from a star where a planet could theoretically maintain liquid water on its surface. Not too hot, not too cold, just right. The term comes from the fairy tale, and the analogy is obvious. 3 bowls of porridge, 3 planets, one of them the right temperature. The idea has real scientific merit. Liquid water is, as far as we know, the essential ingredient for life as we understand it. Every living thing on Earth requires it. And liquid water can only exist on a planet's surface within a specific temperature range, above 0 degrees Celsius and below 100 degrees at standard atmosphere pressure. Too close to the star, and the water boils away. Too far, and it freezes permanently. For our solar system, the habitable zone sits roughly between 0.95 and 1.37 astronomical units from the Sun-Earth orbits, at exactly 1 astronomical unit. Venus orbits at 0.72. Mars orbits at 1.52, just outside the outer edge of the classic habitable zone, though some calculations include it depending on atmospheric assumptions. So far, so good. Venus is inside the inner edge of the zone. Too close, too hot. Mars is near the outer edge. Too far, too cold. Earth is right in the middle. The theory explains everything neatly, except the moon. But the problem nobody talks about. The moon orbits Earth at an average distance of 384,400 kilometers. Earth orbits the sun at 150 million kilometers. In astronomical terms, the moon is at exactly the same distance from the sun as Earth. It receives the same solar radiation per square meter. By every measure that the Goldilocks zone uses to define habitability, the moon qualifies. And the moon is one of the deadest objects in the inner solar system. No atmosphere, no liquid water, no magnetic field, no geological activity, no carbon cycle, no plate tectonics. A surface temperature that swings by 300 degrees between day and night because there is nothing, no atmosphere, no ocean, to retain or distribute heat. The Goldilocks Zone explains nothing about the moon, because the moon is in it, and it is dead. This is not a minor inconvenience for the theory. This is a fundamental problem. If distance from the sun were the primary determinant of habitability, the moon should be habitable, or at least should have been at some point in its history. It never was. Not even close. And the moon is not the only counterexample. Europa, one of Jupiter's moons, orbits at 5.2 astronomical units from the sun deep inside what is normally described as the frozen outer solar system, far beyond the outer edge of the habitable zone. And yet Europa almost certainly has a liquid water ocean beneath its ice shell. A liquid water ocean larger than all of Earth's oceans combined, sustained not by solar radiation, but by tidal heating, the gravitational flexing of the moon's interior as it orbits Jupiter. Life may exist in that ocean right now. Europa is not in the Goldilocks zone, not even close. And Enceladus, a tiny moon of Saturn, 9.5 astronomical units from the sun, has active hydrothermal vents on its ocean floor and has been found to be actively venting water vapor, organic compounds, and molecular hydrogen into space through cracks in its ice shell. All the chemical ingredients for life. In a moon the size of the United Kingdom, at nearly 10 times Earth's distance from the sun, the Goldilocks zone is not wrong. Being at the right distance from a star does provide a starting advantage, the right baseline temperature for liquid water to potentially exist on the surface. But it is, at best, a necessary condition. It is absolutely not a sufficient one. And tonight we are going to find out what the sufficient conditions actually are by following Venus and Mars as they lose them one by one. Before we get to the deaths, let me paint you a picture of the beginning, because this is the part that genuinely astonishes me every time I think about it. 4.4 billion years ago, the inner solar system was a violent, chaotic place. The sun had ignited roughly 100 million years earlier. The planets were forming from the disk of gas and dust surrounding it, dust grains colliding and sticking together, building into pebbles, then boulders, then planetesimals, then planets. The process was violent. Impacts were constant. The inner planets were red-hot from the energy of formation. But by about 4.4 to 4.2 billion years ago, the chaos had started to settle. And what it left behind, in the inner solar system, were 3 rocky worlds at different distances from the sun, Venus, Earth, and Mars, that were, in their broad outlines, remarkably similar. All 3 had thick atmospheres. All 3 had liquid water on their surfaces. All 3 had active volcanic interiors releasing gases into those atmospheres. All 3 were warm, geologically active, chemically complex worlds in the right temperature range for liquid water to exist. A visitor to our solar system 4.2 billion years ago, with the right instruments, would have seen 3 potentially habitable worlds, 3 blue planets with water, 3 candidates for life. We're the only one that made it. And the question is not why we succeeded. The question is what exactly went wrong with the other 2. Because the answer to that question contains the true secret of why Earth is alive. Not distance from the sun, something deeper, something more specific, something that turns out to be terrifyingly contingent. Mars, the planet that died of being too small. Let's start with Mars. Because Mars is the most instructive case. It is the planet whose story most clearly reveals what actually matters for a world to stay alive. Mars today is cold, dry, and almost airless. Its atmosphere is about 1% as thick as Earth's, mostly carbon dioxide, with almost no oxygen and almost no water vapor. Its average surface temperature is minus 60 degrees Celsius. Its surface is covered in iron oxide dust, rust, giving it the famous red color. No liquid water has existed on its surface for billions of years. But Mars was not always like this, and the evidence for what it once was is written all over its surface, if you know how to read it. The Mars we can read today, through the observations of dozens of spacecraft and rovers, tells a completely different story from the Mars we see now. The surface of Mars is covered in geological features that can only be explained by the presence of flowing liquid water. Ancient river valleys, some of them comparable in scale to the Amazon basin, carved by rivers that flowed for millions or hundreds of millions of years. Dried lake beds with the characteristic sediment layering of bodies of standing water. River deltas, the fan-shaped deposits where rivers slow and drop their sediment load as they enter a larger body of water, that are structurally identical to river deltas on Earth today. These features require liquid water, lots of it, for a long time. NASA's Curiosity rover, operating in Gale Crater, found evidence of an ancient lake system that existed for potentially millions of years and contained water with a chemistry that would have been hospitable to life as we understand it. The pH was near neutral. The temperature was moderate. The chemical energy sources were present. If you had put microbial life from Earth into that ancient Martian lake, it might well have survived. And above the surface evidence, there is the atmospheric evidence. Mars's thin atmosphere has a specific chemical signature, a ratio of different isotopes of carbon, oxygen, and argon that matches what you would expect from an originally thick atmosphere that was gradually stripped away over billions of years. The atmosphere we see on Mars today is the remnant of a much richer atmosphere that once existed. We can measure what was lost. NASA's MAVEN mission, the Mars Atmosphere and Volatile Evolution spacecraft, which has been orbiting Mars since 2014, has measured the rate at which Mars is currently losing its atmosphere to space. From that rate, and from the atmospheric chemistry, scientists have reconstructed the history. Mars once had an atmosphere thick enough to maintain liquid water on its surface, and that atmosphere was stripped away. The question is how, and when, and why. The first domino, the magnetic field. The answer begins with the magnetic field. Earth has a global magnetic field. You know this because compasses work. The field is generated by convection currents of liquid iron in Earth's outer core, a process called the geodynamo. The liquid iron, driven by heat from the inner core and from radioactive decay in the mantle, flows in complex patterns. Those flowing electrical currents generate a magnetic field that extends tens of thousands of kilometers into space, forming the magnetosphere, an invisible bubble that deflects most of the solar wind before it can reach the upper atmosphere. The solar wind is a continuous stream of charged particles, mostly protons and electrons, flowing outward from the sun at hundreds of kilometers per second. Without a magnetic shield, those particles would continuously strike the upper atmosphere, transferring energy to atmospheric molecules and accelerating them to escape velocity. Over time, the atmosphere would be stripped away, atom by atom. Mars had a magnetic field. This is not speculation. It is written in the rocks. NASA's Mars Global Surveyor mapped the magnetic signatures of the Martian crust and found ancient rock formations that are strongly magnetized in patterns consistent with a once active global magnetic field. The crust of Mars is, in places, a fossil record of a planetary magnetic field that no longer exists. Just as iron filings align with a magnetic field when molten rock solidifies, the iron-bearing minerals in ancient Martian lavas aligned with Mars's magnetic field as they cooled. And then that field switched off, and the record of it was frozen into the rock. The best current evidence, including analysis of the famous Allen Hills 84001 meteorite, a piece of Mars that was blasted off the surface by an ancient impact and eventually landed in Antarctica, suggests that Mars had a magnetic field that persisted until approximately 3.9 to 3.7 billion years ago. A study published in Science Advances, using a quantum diamond microscope capable of detecting extremely faint magnetic signals in the meteorite's iron sulfide minerals, found evidence that a magnetic field was still active around 3.9 billion years ago, stronger than many previous estimates had suggested. And then it died. Scientists now have a very specific explanation for why it died. A study published in Nature Communications by a team led by Professor Kei Hirose from the University of Tokyo found that the key was the chemistry of Mars's core. Mars's core contains iron mixed with sulfur and hydrogen. At the temperatures and pressures in Mars's core, these materials can separate into two immiscible liquids, like oil and water. The iron-sulfur-rich liquid and the iron-hydrogen-rich liquid don't mix well. As the core cooled, these liquids began to separate and stratify. When the liquids were mixed, the temperature differences between them drove convection, fluid rising and falling, generating the electrical currents that produce the magnetic field. But once the stratification began, the convection current stopped. The two liquids settled into layers. And without convection, the magnetic field collapsed. This separation process was triggered by cooling. And cooling was triggered by size. Mars is about half Earth's diameter and about 10% of Earth's mass. Smaller objects have a higher surface area to volume ratio, meaning they lose heat faster relative to their total heat content. A small rock cools faster than a large rock placed in the same environment. The same principle applies to planets. Mars, being significantly smaller than Earth, lost its internal heat faster. Its core cooled to the point where the iron-sulfur-hydrogen stratification could begin. The convection stopped. The magnetic field died. And from that moment, approximately 3.9 to 4.2 billion years ago, Mars was exposed. What happened next was rapid by geological standards, catastrophic by any standard that matters. The sun in its early history was more active than it is today. It rotated faster. It produced stronger solar wind. It emitted more intense ultraviolet and X-ray radiation. A young, magnetically active sun blasting a suddenly unprotected Mars. NASA's MAVEN mission found that Mars lost most of its carbon dioxide-dominated atmosphere to space about 3.7 billion years ago. The principal investigator of the MAVEN mission stated, "We think that all of the action took place between about 4.2 to 3.7 billion years ago. Within that 500 million year window, the atmosphere was stripped away. The solar wind stripped away most of the Martian atmosphere in only a few 100 million years after the planet lost its magnetic field. The mechanism was specific and relentless. The solar wind, now able to reach the upper atmosphere directly, picked up ionized atmospheric molecules and swept them away into space. Extreme ultraviolet radiation from the sun split water molecules in the upper atmosphere into hydrogen and oxygen. The hydrogen, being very light, escaped to space. The oxygen either escaped or reacted with surface rocks, oxidizing the iron in the Martian crust to form the iron oxide that gives Mars its red color. The rust on Mars's surface is partly the remains of its ancient water, chemically transformed. As the atmosphere thinned, atmospheric pressure dropped. And here is the key physical connection that most explanations skip over. Liquid water can only exist at the surface of a planet if the atmospheric pressure is high enough. At sufficiently low pressure, water transitions directly from solid ice to water vapor without ever becoming liquid, a process called sublimation. As Mars's atmospheric pressure fell below a critical threshold, liquid water became physically impossible at the surface. Any ice that warmed would sublimate directly into the thinning air. The ancient rivers and lakes could not refill. They dried permanently. The temperature also dropped as the atmospheric greenhouse effect weakened. The thick carbon dioxide atmosphere that had kept Mars warm enough for liquid water was being stripped away. As it thinned, Mars lost its insulating blanket. The surface temperature fell. The remaining water locked into ice at the poles and in the subsurface. Within perhaps 500 million years of losing its magnetic field, Mars had gone from a world with rivers and lakes and a thick atmosphere, a world that might have hosted life, to the cold, dry, almost airless desert we see today. And the original cause of all of it was size. Mars was too small. Its interior cooled too fast. Its magnetic field died too early. The rest followed inevitably. Before we leave Mars, I want to tell you something that most people do not know. Mars has not completely given up. In 2024, research based on seismic data obtained by NASA's InSight lander found strong evidence that Mars harbors a large reservoir of liquid water deep under its surface, within fractured igneous rocks at depths of 11.5 to 20 kilometers. The estimated volume of this underground water is enough to fill an ocean that would cover the entire surface of Mars to a depth of between 1 and 2 kilometers. Mars did not lose all its water. It buried it, deep enough to escape the solar wind, deep enough to remain liquid despite the frozen surface. Deep in the fractured rock of the Martian crust, warmed by the residual heat of the planet's interior, there is water, potentially a lot of it. And where there is liquid water deep underground, around any remaining geothermal activity, there is the possibility, not the certainty, but the genuine scientific possibility, that something is still alive on Mars. Not on the surface, not anywhere a rover could easily reach, but in the deep subsurface, in the dark, in conditions not entirely unlike those of Earth's deep ocean hydrothermal vent ecosystems. We have not ruled out life on Mars. We have not even come close to ruling it out. We simply have not looked deep enough yet, and we may not have the technology to look deep enough for decades. Mars is a cautionary tale, but it may not be a completely dead one. Venus, the planet that had 3 billion years and still failed. Now, let us turn to Venus. And this is where the story becomes genuinely unsettling. Because Venus's story is not a story of dying young. It is a story of dying late, of being almost exactly like Earth for almost exactly as long as life has existed on Earth. And then, in geological terms, suddenly and catastrophically failing. Venus today is the most hostile environment in the inner solar system. Its surface temperature averages 465 degrees Celsius, hot enough to melt lead. Its atmosphere is 90 times thicker than Earth's. The pressure at the surface is equivalent to being 900 meters deep in Earth's ocean. The atmosphere is almost entirely carbon dioxide with clouds of concentrated sulfuric acid. The Soviet Venera landers, the only spacecraft ever to survive landing on Venus, lasted between 23 minutes and 2 hours before being destroyed by the heat and pressure. Venus is a furnace, an almost perfectly sealed furnace, with a greenhouse effect so extreme that every attempt to cool down is immediately overwhelmed by the heat trapped in the dense atmosphere. But it was not always this way, and the timeline of when it changed is extraordinary. Venus is 95% of Earth's diameter, 81% of Earth's mass, close enough in size that it retains its internal heat on a similar timescale to Earth. It has active volcanoes, or at least had very recent volcanic activity, with evidence suggesting ongoing eruptions. It has a similar bulk composition to Earth. From a distance, for a billion years ago, Venus and Earth were remarkably similar worlds, and the evidence suggests Venus may have had liquid water. The clearest chemical fingerprint comes from the ratio of deuterium to hydrogen in Venus's atmosphere. Deuterium is heavy hydrogen, a hydrogen atom with an extra neutron. Because regular hydrogen is lighter, it escapes from an atmosphere more easily than deuterium when the atmosphere is being stripped by radiation or lost to space. So if a planet had water and lost it, the ratio of deuterium to hydrogen in the remaining atmosphere should be higher than in water that was never lost, because the regular hydrogen left while the deuterium stayed. Venus's deuterium to hydrogen ratio is approximately 150 times higher than Earth's. 150 times. That is an enormous signal. It means Venus lost a very large amount of water over a very long time. Water that was once there and is now gone. Computer climate modeling by researchers at NASA's Goddard Institute for Space Studies found that Venus could have maintained a stable, temperate climate for up to 3 billion years after its formation. Not a desert, not a furnace. A world with shallow oceans, moderate temperatures, ranging from about 20 to 50 degrees Celsius, and a stable climate driven by slow rotation and cloud dynamics. A world where life, if it had emerged, could have survived and evolved for 3 billion years. 3 billion years. To put that in perspective, the first unambiguous evidence of complex multicellular life on Earth dates to roughly 600 million years ago. The first animal-like creatures, the first creatures with eyes, the first creatures with limbs, all within the last 600 million years. Life had 3 billion years on Earth before it produced anything more complex than single-celled organisms. Venus had 3 billion years of potentially habitable conditions. Whatever happened to end them happened. The exact moment Venus died. The best current scientific evidence points to a specific type of event that ended Venus's habitable period, a massive volcanic resurfacing event that occurred approximately 700 million years ago. Give or take a few hundred million years. Research published in Geophysical Research Letters suggests Venus may have remained habitable until as recently as 715 million years ago. To understand why this was catastrophic, you need to understand something about how Earth keeps its climate stable. Earth has what scientists call the carbonate-silicate cycle, or more simply, the carbon cycle. Here is how it works. Carbon dioxide is released into the atmosphere by volcanoes. It dissolves in rainwater to form carbonic acid. That carbonic acid falls on rocks and chemically weathers them, releasing calcium and other minerals into rivers and eventually the ocean. In the ocean, marine organisms use that calcium and dissolved carbon dioxide to build shells, calcium carbonate, which sink to the seafloor when those organisms die. Over millions of years, the seafloor sediment is subducted, pushed under the continents at tectonic plate boundaries, back into the mantle. In the mantle, at high temperatures and pressures, the calcium carbonate breaks down, releasing the carbon dioxide again, which comes back out through volcanoes. And the cycle continues. This cycle is a planetary thermostat. If the climate gets too hot, more water evaporates, more rain falls, more rock is weathered, more carbon dioxide is pulled out of the atmosphere, and the temperature drops. If the climate gets too cold, less rain falls, less rock is weathered, carbon dioxide accumulates from ongoing volcanic outgassing, and the temperature rises. The cycle self-regulates, and it has kept Earth's temperature within a range suitable for liquid water for essentially its entire geological history. The cycle requires two things: water and plate tectonics. Water drives the chemical weathering of rocks. Plate tectonics recycles the carbon-bearing sediment back into the mantle so it can be released again. Without either of these, the cycle breaks. Carbon dioxide accumulates in the atmosphere without being removed. Temperatures rise, and they keep rising. On Venus, approximately 700 million years ago, something broke the cycle catastrophically. The most compelling hypothesis is large-scale volcanism, what geologists call a large igneous province event, on a scale that dwarfs anything in Earth's recorded geological history. Imagine hundreds or thousands of volcanic eruptions happening simultaneously or in rapid succession over a geologically brief period, releasing enormous quantities of carbon dioxide into the atmosphere all at once. Similar events have happened on Earth. The Siberian Traps, a massive volcanic event that occurred approximately 252 million years ago in what is now Siberia, released enough carbon dioxide and other gases to cause the Permian-Triassic mass extinction, the worst mass extinction in Earth's history, which killed roughly 90% of all species. That event unfolded over perhaps 1 million years. The event on Venus appears to have been larger. And Venus had one crucial difference from Earth. By 700 million years ago, Venus may have already lost most of its plate tectonic activity, removing the one mechanism that could recycle the carbon dioxide back out of the atmosphere. Here is the sequence, as best as scientists can reconstruct it. The massive volcanic event releases an enormous pulse of carbon dioxide. Temperatures begin to rise. As temperatures rise, oceans begin to warm. As the oceans warm, they release more dissolved CO2. As the atmosphere thickens with CO2, more heat is trapped. The greenhouse effect strengthens. Temperatures rise further. More ocean water evaporates, adding water vapor, another powerful greenhouse gas, to the atmosphere. The atmosphere becomes denser and hotter. More ocean evaporates. At some point, this process becomes self-sustaining. It no longer needs the initial volcanic input to continue. The warming drives more evaporation, which drives more warming, which drives more evaporation. This is a runaway greenhouse effect. And once it begins, it does not stop on its own. Water vapor rose high into the Venusian atmosphere. Ultraviolet radiation from the sun split the water molecules into hydrogen and oxygen. The hydrogen, being very light, escaped to space permanently, which is why Venus's deuterium to hydrogen ratio is 150 times Earth's. The oxygen reacted with surface rocks, oxidizing them. The water was gone, permanently. And with the water gone, the carbon cycle, which requires water, could not remove the carbon dioxide from the atmosphere. The CO2 just accumulated. By the time the process had run its course, Venus had an atmosphere 90 times thicker than Earth's, almost entirely carbon dioxide, trapping so much heat that the surface temperature stabilized at 465 degrees Celsius. The oceans were gone. The surface was being continuously reshaped by volcanic activity without any water to weather the rocks. The carbon cycle was dead. The thermostat was broken, and it has been broken for roughly 700 million years. The catastrophe that ended Venus was volcanic. Not distance from the Sun, Venus was in a similar orbital position for 3 billion years before the catastrophe. The catastrophe was internal. It was geological. It was the loss of the mechanisms that maintain stability. Was Venus always dry inside? There is a second hypothesis about Venus that is darker in some ways. Research published in 2024 in Nature Astronomy by a team from the University of Cambridge suggested that Venus may never have had a water-rich interior, and that this, rather than the volcanic resurfacing event, explains its fate. The argument goes like this. On Earth, volcanic gases are more than 60% water vapor. This reflects Earth's water-rich interior, water that was incorporated into the planet's mantle during formation and is slowly released through volcanic activity. This water-rich volcanic outgassing is part of what sustains the carbon cycle and keeps the surface wet. The Cambridge team calculated that volcanic gases on Venus are no more than 6% water vapor, roughly 10 times drier than Earth's volcanoes. This suggests that Venus's interior, the source of its volcanic activity, is extremely dry. And if the interior is dry, then Venus may never have had a water-rich surface. It may never have had the deep oceans that the climate models suggest. In this version of the story, Venus and Earth were never as similar as we thought. Venus formed with less water in its interior from the beginning, which meant its volcanoes outgassed less water, which meant its surface had less water, which meant the carbon cycle was always weaker, which meant it was always more vulnerable to a greenhouse runaway. The two hypotheses are not fully mutually exclusive. Venus may have had a drier interior than Earth from the start, giving a less stable carbon cycle, while a massive volcanic event 700 million years ago, was the final trigger that pushed it past the point of no return. The interior dryness made it vulnerable. The volcanism executed the sentence. Either way, the conclusion is the same. What killed Venus was not its distance from the Sun. What killed Venus was geology. The loss of the mechanisms, plate tectonics, a water-rich interior, a functioning carbon cycle, that would have kept it stable. The Moon, Theia, and the catastrophe that saved everything. We established in the opening that the Moon destroys the Goldilocks theory. The Moon is at the right distance from the Sun and is utterly dead. But the Moon is actually more than a counterexample to a flawed theory. The Moon is one of the specific reasons Earth is alive. And the way it came to be part of our story is one of the most violent events in Earth's history. Approximately 4.5 billion years ago, roughly 50 to 100 million years after Earth formed, the early Earth was struck by a planetary body roughly the size of Mars. Scientists have named this body Theia, after the Greek Titan who was the mother of the moon goddess. The impact was not a gentle collision. Theia struck the proto-Earth at an oblique angle at several kilometers per second. The energy released was incomprehensible. The outer layers of both Theia and the early Earth were vaporized and blasted into orbit. The iron cores of both bodies merged, sinking to the center of the combined object. The ejected material, a disk of vaporized rock circling the newly enlarged Earth, gradually coalesced under gravity into what became the Moon. The evidence for this impact is overwhelming. The Moon's composition is extraordinarily similar to Earth's mantle. The same isotopic ratios, the same minerals, the same oxygen isotope signatures. The Moon has almost no iron core, because most of the iron from both impacting bodies merged into Earth's core during the collision. And the Moon's overall density is lower than Earth's for the same reason. This was a catastrophe of almost unimaginable violence. And it may have been the event that gave Earth the internal structure that has sustained life for 4.5 billion years. The merger of Theia's iron core with Earth's proto-core increased Earth's total mass significantly and gave it a larger, hotter iron core than it would otherwise have had. This larger, hotter core has been a critical factor in sustaining Earth's magnetic field for 4.5 billion years. Mars, with its smaller mass, cooled faster. Earth, partly because of the mass it gained from Theia, has been able to sustain convection in its outer core continuously, generating the magnetic field that has protected the atmosphere throughout Earth's history. The impact also appears to have mixed the interior of the early Earth significantly, contributing to the chemical composition of the mantle that makes plate tectonics possible. Earth's plate tectonics depends on specific properties of the mantle: its viscosity, its water content, its temperature gradient. The Theia impact, by mixing and reorganizing the early Earth's interior, may have contributed to producing exactly the mantle composition that makes plate tectonics work. And the Moon itself, the direct product of the impact, has been a stabilizing force for Earth's climate throughout its history. Earth's axis is currently tilted at 23.5 degrees relative to its orbital plane around the Sun. This tilt is what gives us seasons. When the northern hemisphere is tilted toward the Sun, it receives more direct sunlight and experiences summer. When it is tilted away, it receives less and experiences winter. The tilt of Earth's axis is not fixed. Like a spinning top that wobbles slightly, Earth's axial tilt varies over long cycles, a process called obliquity variation. Currently, Earth's obliquity varies between about 22.1 and 24.5 degrees over a cycle of roughly 41,000 years. This variation is small and gentle. It contributes to the Ice Age cycles that have shaped Earth's climate over the past few million years, but it is not destabilizing. The reason the variation is so small is the Moon. The Moon's gravitational influence on Earth stabilizes the axial tilt, preventing it from wandering to extreme values. Computer simulations of what Earth's axial tilt would do without the moon consistently show that it would vary chaotically, not between 22 and 24 degrees, but potentially between near zero and over 85 degrees, over timescales of tens of millions of years. What would happen to Earth's climate if its axial tilt varied to extreme values? At near zero tilt, there would be almost no seasons. The poles would be in permanent twilight and would freeze permanently. At very high tilts, 60, 70, 85 degrees, the poles would face the sun directly for months at a time, while the equatorial regions would be in prolonged darkness. The climate consequences would be extreme. Ice ages of a severity that would dwarf anything in Earth's geological record. Periods of such intense polar heating that the ice caps would melt completely, flooding the coastlines. Rapid swings between these extremes. Complex life that requires stable environmental conditions over millions of generations to evolve, would face almost impossible challenges under such conditions. Mars, without a large, stabilizing moon, has experienced exactly this kind of axial chaos. Mars's obliquity has varied enormously over its history, from near zero to over 60 degrees, according to computer simulations. This would have produced violent climate swings on Mars even before the loss of its atmosphere and magnetic field, contributing to the instability that made its situation so precarious. The moon did not just form by accident. The moon formed because of a catastrophic impact that almost destroyed Earth. And that catastrophic impact turned out to be one of the key events that kept Earth stable and habitable for 4.5 billion years. The violence that created the moon also made the moon necessary. And the moon's existence has been quietly, invisibly, stabilizing Earth's climate ever since. What actually keeps a planet alive? The four conditions. We have now followed Venus and Mars to their deaths. We have seen the moon be born, and we are ready to answer the real question. What actually keeps a planet alive? Not distance from the sun, not being in the Goldilocks zone. What specific physical conditions have to be met and maintained simultaneously, continuously, for a rocky planet to support life over billions of years? The answer is four things. For conditions that Earth has met continuously for 4.5 billion years that Venus and Mars each failed to maintain. And the terrifying thing, which we will get to at the end, is that none of them are permanent. Earth is still meeting all four. For now. The size. A planet must be large enough to retain its internal heat for long enough for life to emerge and persist. Smaller planets lose heat faster because they have more surface area relative to their volume. The moon, at 1.2% of Earth's mass, lost its internal heat extremely quickly, within the first few 100 million years of its existence. It never had a sustained magnetic field, never had sustained volcanic activity, never had the internal energy to drive plate tectonics. Mars, at 10% of Earth's mass, did better. It was large enough to maintain a magnetic field and an active interior for perhaps the first billion years of solar system history, but not large enough to sustain them beyond that. The cooling of the Martian interior and the resulting stratification of its core that ended its magnetic field was, fundamentally, a consequence of being too small. Earth, at its current mass, appears to be close to the minimum size needed to sustain a continuously active magnetic field over geological timescales. A significantly smaller Earth might have cooled faster, lost its field earlier, and ended up more like Mars. The fact that Earth was large enough, partly because of the mass it gained from the Theia impact, may be one of the most fundamental reasons we exist. Size is not the only factor. The composition of the interior matters too, specifically the presence of radioactive isotopes in the mantle. Uranium-238, thorium-232, and potassium-40 release heat as they decay, providing a sustained internal heat source that slows the overall cooling of the planet. Earth has enough of these radioactive isotopes in its mantle to provide roughly 20 terawatts of internal heat, contributing to the sustained convection in the outer core that generates the magnetic field. But size determines the ratio of heat generation to heat loss, and Earth's size puts on the right side of that ratio. The magnetic field. A planet must have a global magnetic field strong enough to deflect the solar wind and protect its atmosphere. We have seen what happens without one. Mars lost its magnetic field roughly 4 billion years ago. Within 500 million years, the solar wind had stripped most of the Martian atmosphere. Without the atmosphere, liquid water could not exist on the surface. The rivers dried. The lakes evaporated. The planet froze. Earth's magnetic field is generated by the convection of liquid iron in the outer core. The outer core remains liquid because the temperature difference between the solid inner core and the liquid outer core, driven by the heat released as the inner core slowly solidifies and by radioactive decay in the surrounding mantle, maintains the convective currents that generate the field. This is not a simple, stable system. Earth's magnetic field reverses its polarity on irregular timescales. The north and south magnetic poles switch, typically over a period of thousands of years, roughly every 200,000 to 300,000 years on average. During reversals, the field weakens significantly. It does not disappear entirely, but becomes more complex and less well organized, with multiple weaker magnetic poles rather than a single strong global field. During these transitional periods, more cosmic radiation reaches the surface and more atmospheric molecules are vulnerable to solar wind stripping. But the field has never disappeared entirely. Not in 4.5 billion years. It has weakened, reversed, reorganized, but it has never failed catastrophically in the way that Mars's field failed. Earth has been continuously protected from the solar wind throughout its history, and that continuous protection has been essential to maintaining the atmosphere, which has been essential to maintaining liquid water, which has been essential to maintaining the carbon cycle, which has been essential to maintaining stable temperatures. The chain connecting the magnetic field to the existence of life on Earth's surface is specific and unbroken. Every link matters. Break any one of them, and the chain fails. Plate tectonics. A planet must have active plate tectonics to recycle carbon and regulate its long-term climate. Earth is, as far as we currently know, the only rocky planet in the solar system with active plate tectonics. Venus does not have it. Mars lost it billions of years ago. Mercury never had it. The Moon never had it. Plate tectonics is driven by heat. The heat in Earth's mantle, from residual formation heat from the Theia impact and from ongoing radioactive decay, drives convection in the mantle rock. The hot rock rises, spreads, cools, and sinks back down. Where plates spread apart, new seafloor is created from upwelling magma. Where plates converge, one plate sinks beneath the other, a process called subduction, carrying the seafloor sediment down into the mantle. This subduction is the critical step in the carbon cycle. The calcium carbonate sediment on the ocean floor, the shells and skeletons of billions of years of marine life, is carried down into the mantle, where heat and pressure break it down into calcium and carbon dioxide. The carbon dioxide eventually makes its way back to the surface through volcanic eruptions. The calcium stays in the mantle. The cycle continues. Without subduction, the carbon that goes into the ocean floor sediment stays there. It is not recycled. Carbon dioxide from volcanic outgassing accumulates in the atmosphere without being removed by the carbon cycle. On a short time scale, this would cause warming. On a geological time scale, millions to billions of years, it could drive a runaway greenhouse effect, as appears to have happened on Venus when its plate tectonics slowed or stopped. There is an additional subtlety here that makes plate tectonics even more important. Plate tectonics is only possible on Earth because of the specific physical properties of Earth's mantle. its viscosity, water content, and temperature. Water in the mantle is critical. It lowers the melting point of rock and reduces its viscosity, making it easier for plates to slide and subduct. A dry mantle would be more rigid and resistant to plate movement. And water in the mantle comes, ultimately, from water that is carried down into the mantle by subducting plates from the very process of plate tectonics itself. This creates a self-sustaining system. Plate tectonics carries water into the mantle, which keeps the mantle wet, which keeps plate tectonics possible. But it also means that if plate tectonics ever stopped, the mantle would eventually dry out, making it harder to restart. And on Venus, with its dry interior, this may be exactly what happened. A planet that lost its plate tectonics and could never get it back. The right amount of water in the right place. A planet must have water, not just on the surface, but incorporated into its interior, released slowly through geological activity over billions of years. Earth's water did not all arrive on the surface at once and stay there. Earth's water cycles continuously between the surface, the atmosphere, the ocean, the rock, and the mantle. Water is carried into the mantle by subducting plates. Water is released from the mantle through volcanic outgassing. The mantle itself contains significant amounts of water, possibly as much water as all of Earth's surface oceans combined, stored in the molecular structure of mantle minerals. This deep water reservoir is what keeps Earth's volcanoes releasing water-rich gases. More than 60% of the gases released by Earth's volcanoes are water vapor. This ongoing release of water vapor sustains the hydrological cycle, sustains the chemical weathering of rocks that drives the carbon cycle, and sustains the liquid water on the surface. Compare this to Venus. The Cambridge study finding that Venusian volcanic gases are no more than 6% water vapor suggests that Venus's mantle is extremely dry. Whatever water Venus had, and the deuterium to hydrogen ratio suggests it once had a significant amount, is now gone. The water that was on Venus's surface was split by ultraviolet radiation and lost to space. And without a water-rich mantle to replenish it through volcanic outgassing, Venus could not replace the water it lost. The surface dried. The carbon cycle stopped. The greenhouse effect spiraled. Earth's interior water reservoir has been sustained by plate tectonics, which has continuously carried surface water back into the mantle for 4.5 billion years. This creates another self-sustaining loop. Plate tectonics keeps the mantle wet. A wet mantle sustains plate tectonics, and the whole system keeps producing the water-rich volcanic gases that sustain the surface water cycle. Without this loop, without this continuous internal recycling of water, even a planet with large surface oceans might eventually lose them. Not necessarily to a runaway greenhouse, but to the gradual loss of the systems that maintain and replenish them. Earth has been lucky, if luck is the right word, to maintain all four of these conditions simultaneously for 4.5 billion years. But luck implies randomness. The truth is more specific. Earth's size, its composition, the Theia impact, the resulting structure of its core and mantle, the presence of plate tectonics, the internal water reservoir. All of these were set up in the first 100 million years of Earth's history, and have been maintained through a chain of connected, mutually reinforcing systems ever since. Break any link in the chain, and Earth becomes Mars, or Venus. The actual moment Earth almost became Mars. I want to pause here and tell you something that I think makes everything we have discussed feel more real, more personal, more urgent. Earth has not been on a smooth, uninterrupted trajectory to its current state of comfortable habitability. There have been moments, several of them, recorded in the geological evidence, when Earth came close to failing, when the chain of conditions we just described was under serious strain, when Earth could have become what Mars became, or what Venus became. The fact that it did not is not guaranteed by physics. It is the result of specific events that went in specific directions. And it is worth knowing about those moments, because they tell you something important about how fragile the system actually is. Between approximately 720 and 635 million years ago, Earth experienced what scientists call snowball Earth episodes, periods when the planet was essentially entirely covered in ice, from the poles to the equator. The evidence for this is found in glacial deposits, the geological signatures of glaciers, and rock formations that were, at the time they were deposited, at tropical latitudes near the equator. How did it happen? The best current explanation is a feedback loop that ran in the wrong direction. A reduction in carbon dioxide, possibly caused by the weathering of freshly exposed continental rocks, which absorb CO2, or by changes in volcanic activity, caused temperatures to drop slightly. As temperatures dropped, ice spread from the poles. Ice is highly reflective. It reflects more of the sun's radiation back into space rather than absorbing it. More ice meant more reflection, which meant less heat absorbed, which meant more cooling, which meant more ice. The feedback loop fed on itself until the entire planet was frozen. In a frozen state, the carbon cycle essentially stopped. The ice covered the rocks that normally weather and absorb CO2. Without weathering, the CO2 that volcanoes continued to release accumulated in the atmosphere. Over millions of years, the volcanic CO2 built up until the greenhouse effect was strong enough to begin melting the ice. The melting reduced the reflectivity of the surface. Less ice meant more heat absorbed. More heat meant more melting. Another feedback loop, this time running in the opposite direction, rapidly deglaciated the planet. Earth survived snowball Earth. The volcanic outgassing, driven by plate tectonics and the active interior, eventually rescued the system. But if Earth had been slightly smaller, with a less active interior and weaker volcanic outgassing, the snowball state might have been permanent. A frozen planet, with its water locked in ice, unable to weather rocks, unable to cycle carbon, slowly becoming more stable in its frozen state. A Mars outcome, reached by a different route. Approximately 2.4 billion years ago, an event that scientists call the Great Oxidation event fundamentally changed Earth's atmosphere. Before this event, Earth's atmosphere contained essentially no free oxygen. After it, oxygen became a significant component of the atmosphere for the first time. The source of the oxygen was life, specifically cyanobacteria, single-celled organisms that had evolved the ability to perform oxygenic photosynthesis. By splitting water molecules and using the hydrogen to build organic compounds, while releasing oxygen as a waste product, cyanobacteria were producing oxygen in vast quantities. For a long time, this oxygen was absorbed by dissolved iron in the ancient oceans, rusting it, and producing the banded iron formations that we find in ancient rock sequences worldwide. But eventually, the iron was exhausted, and the oxygen began to accumulate in the atmosphere. The consequences were, in biological terms, catastrophic. Free oxygen is toxic to most anaerobic organisms, organisms that had evolved in an oxygen-free environment. The Great Oxidation event was essentially a mass extinction caused by a biological waste product accumulating to lethal concentrations. But it was also the event that made complex life possible. Oxygen, and in particular the ozone layer that forms in an oxygen-rich upper atmosphere, provides protection against ultraviolet radiation. The ozone layer that protects Earth's surface today from the sun's most energetic radiation is itself a product of life. Life created the conditions that made it possible for life to move out of the ocean and onto land. The Great Oxidation event was a crisis that could have gone differently. On a planet with weaker plate tectonics, less volcanic outgassing, or a different biological history, it might not have happened. And without it, complex life, and ultimately us, might never have emerged. Earth has experienced 5 major mass extinction events in its geological history, periods when a significant fraction of all species on Earth were wiped out in geologically brief periods. The most recent of the Big Five was 66 million years ago, the Cretaceous-Paleogene extinction, caused by the impact of a roughly 10-kilometer asteroid at what is now the Yucatan Peninsula in Mexico. This extinction killed approximately 75% of all species on Earth, including all non-avian dinosaurs. It was a catastrophe of global scale. The most severe was the Permian-Triassic extinction 252 million years ago, the one caused by the Siberian Traps volcanic event. It killed approximately 90 to 96% of all marine species and 70% of terrestrial vertebrate species. It is the closest Earth has come, in at least the past 500 million years, to a mass extinction that could have ended complex life entirely. These events remind us that Earth's habitability is not static. It has been challenged repeatedly, and each time, life has recovered, partly because the four fundamental conditions remained in place through the crisis. The magnetic field held. The atmosphere was not stripped. The carbon cycle continued. Plate tectonics kept running. The crisis was severe but contained. If any of those four conditions had failed during one of those extinction events, the recovery might not have happened. The staggering coincidence of being Earth. Let me now step back and look at the whole picture, because when you put all of it together, the size, the magnetic field, the plate tectonics, the water reservoir, the moon, the Theia impact, the specific timing of everything, what you see is not a simple story of Earth being in the right place at the right time. What you see is a remarkable chain of specific circumstances, each of which was necessary, and none of which was guaranteed. Consider the timing of the Theia impact. The giant impact that created the moon occurred approximately 50 to 100 million years after Earth formed. If it had happened earlier, when Earth's interior was still largely molten and chaotic, the results might have been very different. If it had happened later, after Earth had already differentiated and settled into a stable configuration, the mixing effect on the interior composition might have been less beneficial. The impact happened in a window that appears to have been near optimal for producing an Earth with the internal structure, the specific core size and composition, the specific mantle chemistry that makes plate tectonics and a sustained magnetic field possible. Was this coincidence? Possibly. But it is the kind of coincidence that, when you appreciate its consequences, makes the ground beneath you feel different. Consider the position of Jupiter. Jupiter is the largest planet in the solar system, more than twice as massive as all the other planets combined. Jupiter's gravitational influence shapes the distribution of asteroids and comets in the solar system. In our solar system, Jupiter acts as a partial shield for the inner planets. Its gravity deflects some of the asteroids and comets that would otherwise be on collision courses with the inner solar system. Jupiter is also positioned far enough from Earth not to destabilize Earth's orbit, while being close enough to have cleared much of the potentially hazardous material from the asteroid belt. In many planetary systems discovered around other stars, massive Jupiter-like planets orbit much closer to their stars, so-called hot Jupiters, gas giants that have migrated inward to short-period orbits. In such systems, the inner rocky planets, if they exist at all, would have had their orbits severely disrupted. Earth-like planets in habitable zones, in systems with hot Jupiters, are much less likely to exist. The position of Jupiter, far enough to shield without disrupting, appears to be one of the conditions that allowed Earth to develop as it has. Earth has the right amount of water. Not too much, not too little. Too much water, and the entire surface will be covered by a global ocean, with no continents, no continental weathering, and potentially no plate tectonics. Some scientists have argued that a world entirely covered by ocean, an aquaplanet, might have a much weaker carbon cycle and be less stable climatically than a world with both ocean and land. Too little water, and the surface would be dry, the carbon cycle unable to operate, the atmosphere unable to be regulated. Mars may be an example of a planet that ended up on the dry side, though whether this was because of its small size, its interior composition, or both is still debated. Earth's water content is in a range that provides surface oceans, continental land masses, and a water-rich mantle, all the necessary ingredients for the carbon cycle to function. How did Earth end up with this specific water content? The delivery of water to the early Earth is still an active area of research. The current evidence suggests that much of Earth's water came from carbonaceous chondrite asteroids, a specific type of carbon-rich asteroid that delivered water and organic compounds to the early Earth during a period called the Late Heavy Bombardment, roughly 4 to 3.8 billion years ago. The amount of water delivered, and its timing, and the proportion retained versus lost, depended on the specific configuration of the early solar system, including the positions and properties of Jupiter and Saturn, which influenced where and when asteroids and comets were scattered into the inner solar system. A slightly different solar system architecture might have delivered more water to Earth, or less, or delivered it at a different time when the conditions for retention were different. Earth ended up with the right amount of water in the right place at the right time. This is not guaranteed by any law of physics. It is specific to the history of our solar system. All of this connects to one of the deepest questions in science. Why, if the universe is so vast and so old, have we not found evidence of other intelligent civilizations? The Fermi paradox, the observation that the universe should be full of civilizations given its size and age, yet we see no evidence of them, has many proposed explanations. One of the most sobering is what scientists call the rare earth hypothesis. The idea that the specific combination of conditions that produced complex life on Earth is genuinely unusual, perhaps even extraordinarily rare, in the universe. Not impossible. The universe is vast enough that if the conditions are 1 in a trillion, there are still many planets that meet them, but rare enough that inhabited worlds with complex, intelligent life are far less common than the simple Goldilocks calculation would suggest. Being in the habitable zone is easy. In our galaxy alone, there are estimated to be billions of rocky planets in the habitable zones of their stars. But having the right size, the right magnetic field sustained for billions of years, active platetectonics, the right amount of water in the right place, a large stabilizing moon, a Jupiter in the right position, no catastrophic impacts at the wrong time, all of these simultaneously for billions of years. That is a much more specific requirement. Earth may be rare, not unique. The universe is too large for anything to be truly unique, but rare. And appreciating the rarity of what we have might be the most important thing that comes from understanding why Venus and Mars failed. The uncomfortable truth: Earth is not permanent. I want to end tonight's journey with something that I think is important to sit with, because everything we have discussed, every condition, every mechanism, every system that has kept Earth alive for 4.5 billion years is subject to the same physical processes that killed Mars and Venus. Earth is not permanently habitable. It is currently habitable, and the systems that maintain its habitability are slowly, inevitably, changing. Earth's magnetic field has been measured continuously since the 1840s, when Carl Friedrich Gauss developed the first systematic measurement of the global field. The data from nearly 2 centuries of measurement shows clearly that the field has been weakening. Since 1840, the average strength of Earth's global magnetic field has decreased by approximately 9%. 9% in 180 years. If that rate continued, which is not certain, the field fluctuates. It would take several thousand years for the field to weaken to the point where it began to provide significantly reduced protection. In paleomagnetic data, the magnetic signatures preserved in ancient rocks, shows that Earth's field has been both stronger and weaker than it is today at various points in the geological past. The field is currently in what appears to be a gradual decline. Part of this may be because we are in the early stages of a polarity reversal, a process where the north and south magnetic poles switch places, which happens irregularly, with an average interval of roughly 200,000 to 300,000 years. The last reversal occurred approximately 780,000 years ago. We appear to be overdue. During a reversal, the field weakens significantly, potentially to as low as 10% of its normal strength, before re-establishing itself with reverse polarity. During such a period, protection from the solar wind is reduced. More cosmic radiation reaches the surface. The atmospheric stripping that Mars experienced, while much slower for Earth due to the remaining partial field and the much larger mass of the atmosphere, is real. A prolonged period of severely weakened field, something that has happened in Earth's past and will happen again, is a period of greater vulnerability. The field will not disappear permanently. Earth is large enough and hot enough that convection in the outer core will continue for billions of years. But the gradual cooling of Earth's interior over geological timescales will eventually reduce the intensity of that convection. The field will become weaker on average over billions of years. Not imminently, not in any timescale that matters for human civilization, but eventually. Plate tectonics is driven by heat. As Earth's interior cools over billions of years, the heat driving mantle convection decreases. The vigor of the convection decreases. The plates slow. Subduction becomes less efficient. And eventually, on timescales of billions of years, plate tectonics may slow to the point of ineffectiveness. This will not happen soon. Current estimates suggest plate tectonics will remain active for another 1 billion to 2 billion years at least. But eventually, as the heat driving it continues to drain away, the system will slow. As it slows, the carbon cycle will weaken. Carbon dioxide from volcanic outgassing will not be as efficiently recycled. Atmospheric CO2 will tend to accumulate. Temperatures will tend to rise. At the same time, the sun is getting brighter. Stars like our sun increase in luminosity over their main sequence lifetimes. The sun is currently about 30% brighter than it was when Earth formed. In the future, it will continue to brighten. This means the habitable zone is slowly moving outward, and Earth is slowly approaching the inner edge of the new, brighter habitable zone. The combination of a weakening carbon cycle and an increasing solar output creates a convergent problem. Research published in geophysical research letters suggests Earth will experience a runaway greenhouse effect in approximately 2 billion years as solar luminosity increases to the point where the oceans begin to evaporate faster than the carbon cycle can compensate. This timeline may be shortened if plate tectonics weakens significantly before then. But either way, the outcome is the same. In roughly 1 to 2 billion years, Earth's surface will become uninhabitable. The oceans will evaporate. The carbon cycle will stop. The greenhouse effect will spiral. Earth will become Venus. Not immediately. Not in any time scale that should concern us practically. But the physics is clear. Earth's habitability has an expiration date. The same processes that killed Venus will eventually kill Earth. We are simply earlier in the sequence. Here's the thing that I want you to carry with you as you fall asleep tonight. We exist at a specific moment in Earth's history. Not the beginning. Life has been here for 3.7 billion years before us. Not the end. The planet has at least another 1 billion years of habitability ahead. We exist in what might be called the mature phase of Earth's habitable period. Old enough that billions of years of biological evolution have produced complex life. Young enough that the systems sustaining that life are still running well. This moment, this specific window of billions of years in which complex life can exist on this planet, is not infinite. It is bounded. On one side by the billions of years it took life to become complex enough to understand its own existence. On the other side by the inevitable end of the conditions that make that existence possible. We happen to be alive in the middle of that window. That is not something to take for granted. And if you needed a reason to appreciate the unremarkable miracle of a planet with blue oceans and a breathable atmosphere and a magnetic field and active volcanoes and plate tectonics, a planet where liquid water falls from the sky as rain and collects in rivers that flow to seas, all you need to do is look at what happened to the two worlds closest to us. Venus had it for 3 billion years and lost it. Mars had it for less than 1 billion years and lost it. We have had it for 3.7 billion years and counting. This was Alone with Curiosity. Real science. Deep curiosity. Rest your mind.